Okay, so we can start with the, so we're going to derive the Bernoulli equation. Okay, we're going to start from the Euler equation. Okay, this is the Euler equation with the what's wrong with that? My pressure gradient and my body force expressed as the scalar of a potential. Okay, so this is just my Euler equation. Now we can take this advective acceleration term and express this in the form of vorticity. Okay? So we're going to take this term and do a simple trick. So I've done nothing so far. Then I take away this term and I add it again. Okay, so minus this plus this. This, if you remember, is the rotation tensor. Okay, so that's how we're gonna express it in the form of vorticity. And this term I can move inside the derivative. I can say that this is twice my kinetic energy. Okay, just for convenience. And if you remember, we can express the rotation tensor with the alternating tensor as this and related to the vorticity. Okay, so if I use these two expressions, I have minus J, the alternating tensor, plus my kinetic energy. Okay. Now this term can be shown to be equal to this if you use the properties of the alternating tensor. So now I can plug this back into the Euler equation. Twice my kinetic energy plus the pressure gradient plus my body force and that is going to be equal to my vorticity term. Okay, so now I have expressed the Euler equation in terms of the vorticity. Now we're going to do an assumption, and the assumption is that the flow is barotropic. Assumption that the flow is barotropic means that density only depends on pressure. Okay? So density is a function of pressure only. It's a strong assumption, but we will see that eventually it's going to be a valid assumption because we're going to stay on a streamline. So if we make this assumption, then we can write the pressure gradient as in this form, where this is a perfect, is that right? Is a perfect differential. Okay? Just because we made the assumption of barotropic fluid. So we can take this term and put it back into the Euler equation, where we have now this X of my kinetic energy plus my pressure energy term plus the potential energy term. And all that is going to be equal to the vorticity term. Okay? So what I did is taking the Euler equation, decompose this advective term in a way so that the rotation tensor would arise, and then I wrote the rotation tensor through the alternating tensor with the vorticity vector. Okay? Then I rearranged a little bit, put some things on the left hand side, made the assumption of barotropic flow. Okay? And so now I have the time derivative of the velocity vector is equal to these three terms. So here you see the kinetic energy term, the potential energy term, and this is the pressure energy term. Okay? And that is going to be equal to the vorticity term. Okay? So we can now define this as B, which is the Bernoulli function. So I can finally write this as so this is a new form of the Euler equation with the vorticity vector and with this function B defined to be the Bernoulli function. Okay? And this Bernoulli function has these three energy terms in it. And it is a conservation, it is a statement of conservation of energy, and we'll see how that applies and under which assumptions. The easiest case to see physically what does that mean is make another assumption of steady flow. Okay, so for a steady flow, the d by dt is equal to 0. So we have this. Okay, in a steady flow condition. Now, what does this mean? This is a vector that is normal to the surface B, or constant B, right? And this is a vector that is normal to both U and vorticity. So if you make a sketch of this, you have, this is the vector, which is normal to this surface B. Okay? Which is equal to this vector, which is normal to U and W, which are the streamlines and the vortex lines. Okay? Actually, we'll define the vortex line in a minute, but vortex lines are basically the same thing as the streamlines, but instead of being lines of constant velocity, they are lines of constant vorticity. So imagine this to be a streamline, and if you want, this is a vortex line. They are on the same plane B, vortex line, okay? Because these two are equal. So what does this mean? It means that the surface B contains both the streamlines and the vortex lines on a steady flow. Okay? Because this vector is normal to the surface B, which is this. And this vector is normal to both the streamlines and the vortex line, which have to be on the same plane B. Okay? So we made a few assumptions. Steady flow and barotropic. So assumptions are steady flow, barotropic, and actually we will see that it also has to be inviscid. Okay, no viscosity. Otherwise, viscosity might change the vorticity of the flow. And inviscid flow. So under these assumptions, this function B is a constant along any streamline or vortex line. Okay, so basically this means that if you're following a streamline, this function, this Bernoulli function, will have to be a constant. And so is a way of defining the conservation of energy, okay, along a streamline, under these assumptions of steady flow, barotropic, and inviscid. If you have viscosity, then vorticity might change, and this will not hold anymore. But under this assumption, this function is a constant along a streamline. So if you follow the flow along a streamline, this is a constant. And it's a very useful property because you can use these three terms to diagnose the energy of the system. Okay? And we'll see a few examples. So this is a way of defining the Bernoulli function from the Euler equation. Well, we can also do it from the energy equation, which is we arrive at the same conclusion. And we take the same approximations, so steady flow, barotropic, and inviscid.
Professor,
Yeah.
one question. The integral of dp over rho. What are the extremes of integration? Just reference pressure and pressure at certain depth at the depth of the streamline?
It's along the streamline. So actually you can show, you can look at the bachelor, you can show that it doesn't matter over which circle you integrate, that's a perfect differential, so it doesn't matter. Okay. So if we do it from the first law of thermodynamics and we take the same assumptions, steady, barotropic, and viscid. So if you remember the first law of thermodynamics that we derived earlier, rho GI plus the work done by the surface stresses, and we make all those assumptions. So steady flow, so the d by dt is equal to 0, and then no viscous stresses. Okay, so inviscid. If it's inviscid, you can go back to the constitutive equation, and the constitutive equation has two terms: the static term, the pressure, plus the radiatoric stress tensor. But if it's inviscid, this was proportional to the viscosity. If it's inviscid, this is equal to 0. And then no heat conduction. You don't want to change the heat of the system so that the system is equal to 0. So if we apply all of these assumptions to the first law of thermodynamics, what do we get? We get to, so the Lagrangian derivative just has the advective component because the d by dt is equal to 0. Then we put the potential energy term on the left hand side, and that is equal, so this is only equal to the pressure term P, the Kronecker delta. Okay, this is equal to 0. The potential energy term is gone into the advective derivative, so that's what we're left with, and no heat conduction. This can be rewritten as multiplying by rho dividing by rho. And then I use the Kronecker delta to switch the index. So now I can put this derivative on the left hand side, and I end up with the same form for the Bernoulli function. The rho is here, and the UI as well. Okay. So this is again my Bernoulli function with now the internal energy. So this is telling me that the gradient of B, so the gradient of my Bernoulli function, is normal to the streamline of the direction UI. Okay, so again, this function B is a constant along the streamline. So it's the same statement of conservation of energy, but now through the first law of thermodynamics. How is this useful? In many ways. Okay, so just remember we took those assumptions: steady flow, so the d by dt is equal to 0, inviscid flow, So the constitutive equation for the Newtonian fluid is reduced to that, and no heat conduction. If you take those assumptions and you manipulate your Euler equation, you get to an expression for the Bernoulli function, which is a constant along streamlines. If vorticity is equal to 0, so we had this on a steady state condition, right? If vorticity is equal to 0, so this means that the Bernoulli function is a constant along streamlines or vortex lines. If vorticity is equal to 0, Bernoulli function is a constant everywhere. So this is useful and is used in many applications. Simple hydraulic applications, but also more complicated geophysical applications, okay, in terms of conservation of energy. And this is basically telling you, you can use that in many, we'll make a couple of examples, okay. So what you have in this Bernoulli function B is those three terms, okay. One is the kinetic energy term, the first one, the potential energy term, the GZ, and the pressure energy, okay, P over rho. So that is going to be the total energy, or if you want to consider the internal energy as well, you can have the internal energy as well. And that is going to be a constant along the streamlines. So as you follow your particle along a constant line, along a streamline, all those three terms have to be a constant. Under those restrictions, steady flow, barotropic fluid, and inviscid. Okay? As I say, that it's very hard to satisfy a lot of these conditions in real geophysical flows, but you can make these assumptions under certain conditions. We use Bernoulli functions every day, even in our heating systems at home, even though we don't notice. Okay? So basically, if that is a pipe, what Bernoulli function is telling you is that Bernoulli at point 1, for example, on the left-hand side, is going to be equal to the Bernoulli function on the right-hand side, or at the choke point where P is equal to 2. Okay? So, and if those red lines are the streamlines, then you can compute your pressure energy, P1, your kinetic energy, and your potential energy at every point along the streamline, and those have to be equal. Okay? So, in this example, it's telling you that at P2, the velocity is larger, okay? And if the velocity is larger at P2 because of continuity, okay, and say that pressure energy is the same because you're staying at the same level, so these two terms are equal. Say that your kinetic energy increases because of continuity here, okay? That means that because the Bernoulli function has to be a constant, then the, this is equal at the 2 points, the potential energy. So the pressure energy are different and the kinetic energies are different. So if the kinetic energy here is larger because the fluid increases in speed because of continuity, that means that the pressure energy has to decrease in order for the Bernoulli function to stay constant. Okay? So if you actually want to reduce the pressure on a pipe, what you have to do is to shrink the pipe, okay? Which is a bit counterintuitive, but actually you're going to make the flow go faster, and that, because of the Bernoulli principle, will decrease the pressure energy on the flow. Okay? So this is called the Bernoulli effect. Okay? So the reduction in pressure that occurs when the fluid speed increases. Just because if one goes up, the other one has to go down. Simple example. Okay? So you have a few terms here. Well, first let's make a couple of examples. school example is called orifice in a tank, which is what we all have experienced when we have a big tank. We remove the lid at the bottom, and then the wine hopefully spills off the tank. Okay? So if this is filled with a liquid, and you imagine this to be streamlines of flow exiting the tank, okay, you can compute the speed of the outflow through the Bernoulli function. So the pressure here at the exit is equal to the atmospheric pressure, and the velocity here at u1, whatever, you can make the assumption that it's basically zero. The level of the liquid or fluid will go down, so it's not really static, but it's going relatively slow as compared to the outflow. So you can make the assumption that that is equal to zero. This is the height of your volume. So because of Bernoulli, you have the pressure energy plus the kinetic energy plus GH at 1, but this is equal to 0. That is going to be equal to P2 over rho plus the velocity exit plus, let's say this is 0. Let's say this is the bottom. So nothing. So here the pressure is also the atmospheric pressure. So the two pressures are the same. And so we are left with is simply this is the velocity at which the fluid will spill out of the tank. Okay. And this is actually called, if you remember the high school days, this is called the Torricelli law, okay, which makes the assumption of the Bernoulli function. Okay. So you make the assumption that these are streamlines and Bernoulli is a constant along the streamlines, and so you can follow the path of all these streamlines, and assuming that the velocity is 0 at the top, you know exactly what the velocity is going to be at the bottom, which is just a function of the height of the fluid, of course. Okay? So this is a trivial example, but just using the conservation of energy through the Bernoulli function. A more fun example is what is called the pitot tube. Dates to Mr. Pitot, actually. I don't have a picture. Well, I'll find the picture. So, Pitot was a mathematician, and he wanted to measure the speed of the river Seine in Paris. Okay? And what he did is he used the Bernoulli function. Okay? So, this is the bottom of the river, and this is the river, Seine, with some flow. So what he did, he used a banded tube like this, which he inserted into the water. Okay. And the level of the water increased until a certain level. So we're going to have H1 and H2. Okay? Because of the speed of the flow, there was an increase in the level of the fluid inside of the tube. Okay? So now imagine you have a streamline, and you have a point 1, which is away from the tube, and a point 2, which is right at the entrance of the tube, along the same imaginary streamline. So U2 is equal to 0. Otherwise, the flow will spill out of the tube. Okay? There's actually an equilibrium when the fluid fills until a certain level of the tube, and when the equilibrium is found, then velocity at 2, which is right at the exit of the tube, is equal to 0. So you can use Bernoulli conservation principle to show that the pressure energy at point 1 plus the velocity at point 1, or the kinetic energy at point 1, that is equal to the pressure energy at point 2. The velocity is equal to 0 at point 2, and the two are at the same height. Okay? They are at the same depth of the river. So these two terms, the GH, cancel out. So this means that U1 is 2 U2 minus U1 over rho. Okay, so that's the velocity of the fluid, which is proportional to the difference between the two pressures. Okay? But now you want to be able to measure the velocity of the fluid by the height h2 inside of the tube. So how can you do that? You can use the famous hydrostatic balance. Okay, if you remember the hydrostatic balance, so the pressure here is going to be rho g h1, and the pressure at 2, which could be right here, is going to be rho g h1 plus h2, okay? Because the total column of fluid inside of the tube is h1 plus h2. So U1, if you substitute, is 2 over rho gh1 plus rho gh2 minus rho gh1 2 h2. Okay? So now the velocity U1 is a function only of the height h2, which is the height inside of the tube. So with a simple tube inside of the river, given a height of the fluid inside of the tube, because of Bernoulli conservation of energy along a streamline, you know what the speed of the fluid is. Okay, you just need a simple tube and assume that the flow is steady, it's not viscous, right? But it's a good approximation. Okay. Now you might think that this is a 18th century result, okay, which is true. Okay, it's 19th century. But actually, I used to have a picture, but I'm going to have to find it. Pitot tube are used every day because technology is great, but if technology fails, it could be a problem. So when technology fails, you go back to simple things like Bernoulli principles and Pitot tubes. So I'm going to show you an image of a Pitot tube that you have used even though you don't know. Okay, you see those yellow arrows? They're pointing to Pitot tubes. Okay, so whenever you board a plane, okay, next time you board a plane, you know that the pilot has a supercomputer which is connected to an airport tower. They are checking everything, speed and pressure and altitude and everything. But if the computer on the plane fails, the pilot doesn't have any idea what the speed is going. He needs to go at a certain speed, otherwise, because of aerodynamics, he's going to fall. Okay. So how does the pilot know what is the speed of the plane if the computer fails? Pitot tube. Okay. They have Pitot tubes on the plane, and because of the different pressure, they don't use height, they use the different pressure. They know what is the speed of the flow or the air outside, and so they can relate that to their own speed. Okay, so they use it, and I think they use it regularly to check that the computer is doing okay. Funny, huh?
So in this case, is it measuring the velocity of the airplane
Ah.
or the wind?
Before you say that,
Okay.
I checked,
Okay.
and the Lake
Tana.
Tana is the source of the Blue Nile. The Blue Nile doesn't go through the Lake Tana.
No, it's not the source.
You're wrong.
No, it's not the source. The source is a separate place. It's not.
I found a scientific paper that I'm going to send to you. So there's actually a publication by some Ethiopians, and they say that the Lake Tana is the so the Blue Nile starts from the Lake Tana.
But we know that there is a place with
No, I trust you, but
a sort of stream of Blue Nile, so it goes through Lake Tana, and then it develops gradually to a bigger river. So there is
okay. No, because this paper says that the Lake Tana, so it's a crater, it's a volcanic crater, and there's many small rivers that are filling the Lake Tana. And then from the Lake Tana starts what is called the Blue Nile. Is that correct?
Yeah.
So there are many rivers filling the Lake Tana, and then what is really called the Blue Nile starts from the Lake Tana. It's not that the Blue Nile starts somewhere else and passes through the Lake Tana. Is that right? I just read it quickly, but that's the message I got.
But from my observation when I was there is a clear difference in the water with the lake and the river.
But that might be, so the color you mean,
Yeah.
that might be sediments
Okay.
that are suspended in the surface. Sorry, what was the question?
Okay. My question is, in the airplane, what is the pitot tube? What is it is measuring? The velocity of the airplane or the wind outside?
I think the pitot tube is measuring the difference in pressure,
Okay.
and so it's measuring the relative velocity between the air outside and the plane. I guess it's assuming that.
B plane is greater than.
Yeah, so I guess it's assuming that. I don't know, assuming the winds.
It's not B plane, the velocity of the plane is much greater than the velocity of the plane. You can
So that is equal to 0, right? Or it probably doesn't matter at those scales. At those scales, it probably doesn't matter. If they are comparable, you have a problem. Yeah. So through the difference in pressure, you know the relative velocity, and then you know at which speed you're going. I think we can actually stop here because Viscosity dynamics usually takes me 2 classes, and to do it in 25 minutes it's going to be useless. I think we went too slow this year. Was I fast or slow?
maybe a lot of questions.
No, it was good. No, it's my problem. Don't blame it on you. Or maybe this year I had fewer classes, I don't remember. Because in my notes it says lecture number 10, Vorticity Dynamics, and this is the number 9. So. Well, you'll see vorticity in the second part of the course anyway. That's why I'm not concerned. Okay, so I found the syllabus. So this was just the syllabus. Okay, so just to recap, what we did was, actually this course should be the first course that we do in the diploma program because it starts really from the basics and introduces all the equations that you normally use in every course, especially in the second term. Okay. But because of many reasons, it's not the first course of. So the first part is, it's a basic course, and the first part is the basic of the basic course. Okay. And so we did. Okay, so this is not even. So this is in lesson number 9, dynamics of light. So this is all. So we just introduced the basic principles that you're going to use during the second part of the course and during the following courses. Okay, whenever you do atmospheric dynamics or climate dynamics or ocean dynamics or seismology in the second part, okay, you'll see that you're going to use surface forces, conservation of energy, all those tensors that we use. You're going to, especially in the applied seismology, you're going to use them a lot. So hopefully you will remember where those terms are coming from and where those conservation principles are coming from. And all the things that we've seen so far, they're going to be used in the second part of the course. Okay? So in the second part of the course, you will introduce this, the Coriolis force or acceleration, okay? And that will change this. And that will change your momentum equations. There's going to be an extra term, and there's going to be some changes in the conservation of energy and the dynamics of the system. Okay? And so you will start seeing how the fluid flow is modified by the rotation of the system, and also by the stratification. So forget about the assumptions of barotropic fluid. The fluid is not going to be barotropic. It's going to be what is called baroclinic, so it depends on temperature and salinity. And that will change the dynamics as well. So you will derive basically the same equations, but with the rotation terms. Okay? And so you will end up in this geophysical fluid dynamics equation, momentum, conservation, and energy, okay? In a reduced way, but with for the case of GFD. Okay? And then you will introduce friction, and you'll get to these boundary layers. Okay? And then you will see, starting from the shallow water equations. You remember we just by chance we derived the shallow water equations when we were doing the conservation of mass. Okay. Through those shallow water equations, you can derive all these nice geophysical waves that have interesting names by the guys that discover them. And then you will do instability problems due to, for example, stratification and mixing problems. Okay, and all those are interesting for climate people and solid earth people. Okay? Mixing and instability problems they apply to all kind of geophysical fluids. So, and then if whoever is staying on the climate side, in the second term we'll do atmospheric dynamics and ocean dynamics. And in ocean dynamics, that I'm teaching, we'll take these equations again and we will develop the theories of the large-scale ocean circulation. Okay? So we'll take these Ekman layers and we will see how the Ekman layers they connect to the interior flow and how they set up the large-scale ocean circulation. And you do the same for the atmosphere. So this is basically, building blocks one after the other. You start from very simple principles and then slowly and slowly you put everything together. The exam is written exam. Okay. The exam is easy. The exam is also for the second part is the same philosophy. So For example, you get an equation, the Bernoulli equation, okay? Explain physically what does it mean, what are the assumptions, what each term means, okay, physically, and how did we ended up to this form of the Bernoulli equation, okay? It's not about deriving equations, because that's not the point of the course. It's trying to understand what are these principles and these conservation principles. So, I think I have exams here. The exams. So you get this expression, for example. What does it represent? What is the meaning of each term? Okay, you should know what it is. You should know what each term means, and or you can take this equation, integrate it for a fixed volume, and explain physically each term. Okay, so it's basic stuff. It's nothing. This you should know. Should be fresh. Okay. What is that? What does it mean physically? How can you apply that simple conservation principle? Okay. So it's very simple. I mean, if you've been in class and awake, there should have been any problem. I've seen somebody sleeping every now and then. and the second part is the same philosophy. Okay, so you take. I'm going to give you an expression for the waves, and I'm going to tell you which kind of waves is this, and what are the assumptions, and what does it mean, and so on and so forth. So, don't worry. So the second part is starting next week, and I think he's going to teach like 3 or 4 times per week, something like that, at least next week. 5 times per week.
The first week?
Yeah. 5 times, every day.
Yeah.
Intense.
Got it.
Well, it's good. So you remember things from one day to the other. Old age. So this is me finishing. 1, 2, 3, 4, 5. Enjoy.
Yeah.
Okay. So that's the first week. 5
And 4.
and then 1, 2, 3, 4. Well done. So in 2 weeks, you're done. Okay. And then I think we have the exam before the break. So the 20, right? Yes, we do. You don't know? I think we have the exam on the 21st or 19th or something like that. No?
I'm in Bolzano.
I have to double check, but I'm pretty sure it's before the break. 21st, I think. I don't know. 18th of December. It's even better. Joy in your eyes. Maybe it's not official, but it's going to be 18th of December. It's good because you have everything fresh in your minds, right? No? Do you prefer to wait a month before the exam? So you finish on the 7th, and in 10 days you have the exam. That's perfect. Are you in Bolzano on the 18th?
Yeah.
Yeah, good.
17 and 21.
Just between
5
the
days.
17th
Yeah,
and 21st.
5 days.
Are you going to be here on the 22nd?
Mm-hmm.
You can do the exam.
Okay.
Okay, so yeah. You don't have an excuse. You have to be here.
No, question. It's a question.
Huh?
Question.
Question.
This might be related to hydrostatic buoyancy, but curious why people, when they drown into water, when they are alive, they will sink down if they are not swimming, but as soon as they are dead, they will float up to the surface.
Because they fill up. They fill up with water. I think. Right? No, they inflate. No, they inflate when they're dead. When they're dead, they. That's a nice question. So when they're dead, they should be. Well, you drown, so you take water, so you should go down. You float. Dead bodies.
No, we should sink down.
It depends, because in lakes and rivers, they send the swimmers to find out.
They stay at the bottom.
Yeah.
Well, I mean the buoyancy is different. But why in seawater you gain buoyancy? So you drown, you should have your lungs filled with water. So you should sink.
We should sink, yeah, by enemies.
But then probably when you're dead, I'm thinking of something not nice, but you know, once you die, bacteria, they start doing their job and they produce gas,
But
and that probably fills your tissues.
usually when I look at movies, the people will start to as soon as they are dead, they will come.
Correct.
Sometimes the reason why most people drown is because they are struggling, and that is how they drown. Especially
Well, the reason for drowning is a different question, but once you drown,
once you drown,
Once they are dead by enemies,
They will come out.
They will come out.
Yes.
Even there is no time for bacteria to do something. And
Well, it takes a
doesn't
while.
come immediately.
Well, I think the water can